Okay, good morning, everyone, and thank you for attending this joint webinar between the South African Council for Automation and Control and the South African Institute of Mining and Metallurgy. I'm Anthony Higginson. I'm a lecturer at Wits University, where I work with Dr. Kevin Brooks, who is the presenter of this webinar. To just give you a brief introduction to Dr. Kevin Brooks, he studied chemical engineering at Wits University all the way through, culminating in a PhD in 1986. He then lectured at Wits until 1990 and later joined Honeywell High-Spec Solutions, working in dynamic modeling, APC, which is advanced process control, and optimization. In 2007, Kevin moved to Blue ESP, where together with Anglo Platinum, he pioneered the application of APC in mining. In 2021, he formed his own company, APC Smart, to mentor and train upcoming APC engineers and provide profit improvement programs and project implementation in APC. In 2019, he joined WITS as a visiting and subsequently honorary adjunct professor, and he is the co-leader of the Data Analytics, Numerics, and Control Engineering, or DANCE research group, where he co-supervises 14 graduate students at master's and PhD level. He has been on the ExCo of the South African Council for Automation and Control since 2007, and he was president of SACAC in 2013 and 2014. Last year, he was appointed chair of the International Federation for Automatic Control Industry Committee, which he currently chairs. So over to you, Kevin.
Thank you very much, Anthony. Anthony is involvement, but Anthony is supervising all of those 50 students in that group. And some of the work I'm going to show you comes from students in our group. In particular, and I'll tell you who is who later, Trishkaya, Dumili, and Toboko. I'm presenting some of their results today. Okay. So this is what I want to go through, and we can have questions at the end, and I'm very happy to share the slides as well. I started from the basis that not much is known about the topic. So I'm going to introduce supervised learning as a concept, and also a sort of project management approach to that called CRISP-DM. And then we'll talk about the types of problems that you can address using these techniques and common algorithms, and then a bunch of examples to show you what we can achieve with these tools. I'll talk about the tools available briefly, without recommending any in particular, and give you some conclusions. Okay, so this AI ML thing has become a buzzword in many industries, and there have been many successful implementations, but equally there have been some failures. The tools are out there to do this kind of work and to teach yourself the methods, but it is easy to go down rabbit holes when trying to fit data. So that's just a word of warning. In this talk, because it's such a huge field, in this talk I'm going to concentrate on supervised learning, which is one of the branches of AI ML. What I'm not going to do is present you with any maths or very much at all about the background of the algorithms that we're using. That would just make it too long. So you'll have to trust me that we used what we said we used. So what is artificial intelligence? It's intelligence exhibited by machines as opposed to living beings. And machine learning is a field within that concerned with statistical algorithms that learn from data and generalize to unseen data. So that is why we model. Generally, we model because we want to predict things where we don't have a measurement otherwise. Unsupervised
Kevin, we seem to have lost you.
learning is really the kind of models we're much more used to in kinetics and metallurgy. We're used to models where we know what the inputs and the outputs are. Here's a map from MIT of where we're at machine learning, and this thing just grows from year to year. I've not put it here to talk to it with any great detail, but just to show you that there are other parts of machine learning that we're not going to touch on. We're going to do some of the work over here. We're not going to talk about this, although some of it is associated. We're not going to talk about ensemble learning or really deep learning. And just to mention, reinforcement learning is really the hot topic in control right now. So this is where you allow some system to learn the system you want to control and to generate the control algorithms. And while there are issues around this, this looks to be perhaps 10, 20 years from now, it might be that all our control algorithms, or a lot of our control algorithms, may be based on this reinforcement learning. There are other people in the country who are far better placed to talk about this, including some in the audience. But yeah, we're over here in this corner, and even then we're not going to talk about all of it, so it just keeps growing. I think it's important when you're doing this kind of work to place it in the context of your business. And your business could be a business. In the case of our students, the business is getting a master's or a PhD, but it's still a business. So any work you're going to do must start with a business understanding. Once you've got the business understanding, you can go and look for the data, prepare it, model it with some of the techniques I'm going to talk about or others, and then evaluate how well the model did. At this stage, you may have a recycle back to the business understanding. It might be the evaluation tells you something that you didn't know at the beginning about the business. It might even be something the business doesn't know about the business. So there could be a recycle here. And then finally, you hope that you deploy the solution. Okay. Cross-industry standard process for data mining. There are other models. This one fits on the page nicely. I think it's a very good model to think about what you're doing, and also this step, how important that is. So getting into the supervised learning, there are really two main types of problems that it deals with, and the MIT model shows these. The one is classification, and that is the problem of saying, what if we've got a set of observations, do they belong, can we tell whether they belong to different categories? Okay, so an example in normal life would be, how do you tell whether an email is spam or non-spam? Maybe in our world, is the mill load low, normal, or high? Okay, it might be good enough. You might not need a more complicated model than classifying something as low, normal, and high. And they're very powerful tools for doing that in supervised learning. The regression problem is maybe a little more tough, where you say, I have an output and I want to predict that from a set of inputs. Okay? And then again, we do run into a nomenclature issue. So the dependent variable, which is really control language, or the output, is sometimes called an output, a response, or a label. And the label can be because this thing need not necessarily be a number. It could be cat or dog. And then the independent variables, which are called predictors, covariates, explanatory variables, or features. And I think I'm going to call them inputs. Sometimes it is useful to do classification and get the categories and then do regression. Some of the routines we're going to talk about actually do that for you automatically. So some examples where you might use these techniques in our field. Classification, or classification would be a good one. Can you look at an ore coming in a belt and classify it? Grade determination from images. There's been a lot of work done in this field. Fault detection, is something good or is something normal or bad? And some work that I know is happening at the moment, defining the state of a froth, again from images. So this is different to looking at the grade. It's saying the froth has different states. Okay. For regression, you could be looking at models for grade and recovery. Soft sensors maybe for the grind size from a mill. Could be pellet size distributions. You might want to be characterizing the slag. So those are the kind of problems we can approach with these techniques. There is a very good review out there by John McCoy and Lydia Oret. We really should do another one because a lot has happened in the last 5 years, but this is a very good paper to understand what has been done up to now. Okay. So again, the explosion of techniques which makes a talk like this hard. I'm not going to talk to this again for much, but within supervised learning, you can see within regression, there are these 6. And if you go into the popular packages that do this sort of stuff, there's probably another 20 available. And the same is true for classification. So you have to keep your wits about you as you're doing this work and not go down the rabbit hole. Okay, I'm now going to go through some examples. Some are taken from the literature, and some, as I say, are from the research group that Anthony and I run. And we'll thank the people as we go. And the references for this work are at the back of the paper. So this is a classification example. It's a bit hard to see here, but effectively what the authors did was group a whole lot of running data on a zinc-lead flotation plant and look at the images and look at features of the images and see whether they could classify the lead content based on the images. And this thing is called a confusion matrix. It basically says, how often did I get what I expected to get? And so grade 1 is not terribly good. You only correctly manage to model grade 1 53% of the time, but grade 3 is much better. So this could be very useful. You're looking at your flotation froth and you're saying, what grade category is it in? Now, obviously, as the categories get more and more, eventually you have a continuous model. But these categories were quite wide. So this is an example. This work was done by some Brazilian authors. The paper is very complicated. But I just wanted to show how we present these results, because this is a bit different to how we represent results for continuous data. So remember the confusion. They call it classification results. But overall, they're able to correctly classify 3/4. Now that may not sound a lot, but it might be good enough, particularly since some of the misclassification is only 1 grade away, like here. So you haven't done too bad. Okay. Now, I must be honest, looking for examples of classification or classification used in NNN in the industry, there are some papers, but they're very, very complex, and they're actually very difficult to show the results in a way that is good for a tool. So I'm going to leave classification here as an example. But you might want to think about it when effectively your output is quantized. It could even be red, yellow, blue, like a traffic light. And you want to model them. So the rest of this talk is actually going to be about regression. So measuring the grind from any mill circuit is tricky. There are instruments out there, but they tend to be expensive and, quite honestly, quite finicky. You need a sampling system, and in any case, you need to calibrate. So there's been a fair amount of work done. Can we predict the grind based on the process variables? So this is some grind that we might sample it and measure it in the lab, or it could be a composite sample that we take from a plant. And we collect the lab data over probably a number of months. And we've got the process data from the historian. And can we produce a soft sensor? Can we produce a model? This particular work had 7 months of 12-hourly data. And the features or the inputs that were used included the fresh feed rate, bearing pressures, rotating speed, all the things you'd expect. Mill charge level was inferred in a way. So there was a model, and the cut size was calculated from a cyclone empirical model. So it's quite interesting. So embedded in here, the features, some of them are actually calculated from physical models. It's an interesting approach. So you say to yourself, well, what is actually important? Well, the cut size from the cyclone is going to be important, but I don't have that measured. So I'm going to use a model out there to try and predict it. I can never say the gentleman's name, Nagasarawa, as a model. So they took this data and they put it into 5 different algorithms, popular algorithms: K nearest neighbors, support vector machines, random forests, linear regression, and ADA boost. And I'm not going to go too much into details of it. Those are either. And they got this result, that a boosted tree, ADA boost is a boosted tree. So it's a kind of random forest where so the random forest splits up the data and then fits it. The boosted tree does some clever stuff with the leaves on the tree. It's a very, very bad explanation. Okay. So there is some classification happening here, and then some weights. And unfortunately, they did not present the results in a time series of their data. And I would suggest always do that. But I thought this work was interesting enough that is worth talking about. This work was presented in 2018 at the Cape Town IMPC conference. And they've got root mean squared errors of about 9 on a number that is around 150. So this is pretty good. And you can see the clustering here is good. So this is an XY plot. This is the predicted P80 and the actual P80. It's unusual to do it that way. Normally it's the other way around. And it clusters well around the 45-degree line. And they've done 99% confidence interval. So you'd be very happy with taking this online. This is a good result. And it was worth looking at machine learning techniques because the fit is quite a lot better than, for instance, a linear model. So that's a grinding example. I would call it success. Okay. Now we're moving on to an example, and I think the rest of the examples are, one of them whole plant, but there's a lot of flotation involved. So this is a flotation plant in also lead zinc, as it happens, in Australia, Mount Isa. It's a Glencore operation where myself and my colleagues did MPC work back in mid-2016. And one of the interesting things we did, I think, was we step tested the reagents to this circuit while trying to keep air and level constant. So this should give us the response of the system to the reagents. And recently I threw this data at the MATLAB regression learner tool. Now, this is a tool that will run multiple models for you and report back the results. And this is the primary Roffa-Kohn zinc modeled with time. So this is the time series I was talking about. And just to show you how the picture is important, it's clear that the linear regression hasn't done terribly well. But something called a fine tree, yet another kind of tree solution, has captured the nonlinearities rather well. So these techniques are very useful when you think the behavior is going to be nonlinear. And we have reason to suspect that the response of the system to the reagents is nonlinear. So even this this was done very quickly to give, I've quoted 4 responses, but what I've plotted here are the linear regression and the fine tree. Notice that the data is split into 2 parts, the training set and the testing set. This is very important. I'll show you why just now. So this is where you calculate the regression coefficients, whatever they might be, neural net, doesn't matter. And this is where you say, okay, take some of the data and use my model to predict it. And it's important that you be able to predict it. So this fine tree actually did better on the test data than the training data. That is unusual. And actually all of these look pretty good. But this is to avoid the problem of overfitting. So if you give the data to a regression routine that has too many parameters, you'll find that these things just become blobs. And you may fit your training data very well, but you can't really generalize the result. the data. It is very important to check. And yeah, so we have the nonlinear regression captures some sort of nonlinear behavior, which is interesting. The linear regression doesn't. And we'll come back to this example in a moment. Okay. So my message there is there are tools out there that will do lots of regressions. You still have to think about what you're doing, and you have to use a test set to look at it. Here's another example. This work has been done by Dumili and Meno in our group, and he's looking at a PGM plant where the chrome in the concentrate is very important in terms of what the downstream smelter can cope with. Okay, so he's trying to model the chrome in concentrate, and you'll notice there's no scale here. That's deliberate. And the model doesn't look too bad. It's actually limited data here that is being modeled. But that one was an extra tree. This one is some gradient boost. And here you see that the prediction fails altogether. So you've got to be very careful to make sure your prediction is really a prediction. Much easier with a linear regression to see that sometimes. I'm going to carry on with some work on grades, because I think modeling grades in flotation circuits is something we'd all like to do. This is work being done by Dr. Motza for his masters. Again, it is grades measured on the platinum plant. And this is, as I recall, about 2 years of data. And again, he's testing different algorithms and largely getting good training data. And sometimes the testing looks okay. What we've noticed with this data is at high grades, we're not capturing it. And you can see it here in the fit. So the red is the fit. The green is the test data, by the way. There's a set of test data in the middle there. The blue is the training data. And there's a bunch of kind of high grades. And you'd really like to know why you're getting high grades, but we're not capturing that. So we are still looking at this. But at least you should see a pattern forming. Choose some algorithms, fit them, and look very carefully at the results. You'd think the neural network would do better. It doesn't always. And it is subject to overfitting. And here you get, I've shown these statistics because it kind of puts you in a difficult situation. The neural network in this data has the best root mean squared error and the best R squared. But the support vector machine, even though it's not very good, has the best data for the training set, for the testing set. So what do you do? Well, what you do is you try to bring these closer together. So there's still work to be done here. We are probably lacking some inputs that would help us. One interesting thing about this work that I should have mentioned is that we are using some of the camera data that's available on this plan as inputs. And we'd actually like to start, rather than using the derived camera data, we'd like to use the raw data from the camera as fitting inputs and see if that helps them. So all the models I've shown so far are steady state models. We are taking the data at a particular time. We might average it a little bit back. We might even lag it a bit, but effectively we're doing steady state data. However, in the world I live in of advanced process control, we really need dynamic models. So I thought I'd talk a little bit in my last 5 minutes about that dynamic models. In the linear world, there are very well developed techniques for getting linear models from data, finite impulse response, state space, ARX, autoregressive with exogenous inputs. Nonlinear cases, there are the so-called Hammerstein-Wiener models, where you scale a model according to the nonlinear gain. There's nonlinear ARX, and one that's relatively recent that is getting a lot of popularity. This is a neural net, the long short-term memory. And people have been using it for control. But the key part of this is you need excited data. You need step test data at a high frequency. Okay. Very difficult to get even linear models from non-excited data. It's impossible to get it from non-excited data, but even normally excited data, it is tough. But you can do some stuff. And I wanted to present one example of that. And this is the same data that I presented where I gave you a steady state analysis of the effect of the reagents. At this time, we've done a dynamic model of the system using what's called nonlinear analytics. And this work was done by Shishkaya Harisunka, who I see is on the call, and done very good work on modeling that data set using this nonlinear technique. And this comes from a published paper from an IFAC conference last year, World Conference, and we've certainly got good results using the nonlinear ARX. So this is out on the edge of what you might do as a metallurgist in an operation. Shishka is currently embedding these models in a nonlinear MPC to see how much better you do with a nonlinear MPC than with a linear MPC. Okay. So now, just wanted to talk about tools a little bit. I'm kind of not in the game of selling this stuff or even recommending it. So it's very much my own experience and my students' experience with some of the tools out there. So if you are comfortable with Python, there are many, many libraries out there. They're very good libraries. And you need to understand the supporting tools like NumPy and Pandas and whatever. But the statistical libraries are very good. Okay. There are some analytics platforms out there that we use, or some of which we use. So this RapidMiner, I must admit that the reason we use it is that the company gives academic institutions free access to it. But we've had good results with it as a powerful workflow technique. Seek is very popular. I've never really used it myself. I have used SPSS, and again, it's very powerful, maybe not quite so friendly. MATLAB, again, you have to learn the language, but that regression learner tool, in fact, you don't have to learn the language. to use the regression learner or the classifier apps, but they are kind of a bit black box. So I've put in a little my own advantages, disadvantages, and a lot of it is going to depend on what languages you're comfortable with, what your organization has already available. So MATLAB and the packages have an associated cost, which Python doesn't. Hence its popularity. So, in conclusion, these supervised learning techniques match well with, I think, how we think about the work we do. We like good fits, but sometimes an okay fit is also okay, because it tells us about the important inputs. Beware of overfitting. I know it hurts to throw away part of the data for testing, but it is very important. I haven't talked here about data smoothing or outlier exclusion, but it is very important to look at your data. Very first thing you should do when you get your data is look at it, and then decide what your smoothing, outlier detection, and there are very powerful routines to do that, but always check them. Always check that you have got rid of what you want to get rid of and kept what you wanted to keep. I think this is an advert. We're always looking for good students, Anthony and I, and other people with this. And currently we've got a lot of work in the M area, but also in public data. So we're always looking for good students, and we're always looking for sponsorship. This kind of work is really best done as a collaboration between industry and university, because the industry can supply the data and the process knowledge, and we can do the number crunching. And there are some references that I use during this talk. I'm very happy to take questions.
Thank you very much, Kevin. If anyone has any questions, I think you can put them in the Q&A section or possibly in the chat. I'm not sure if we have an option to have attendees ask their questions specifically.
Hi, Anthony. If anybody wants to ask a question live, I can just unmute them. They can just raise their hand.
Okay, so attendees can also just raise their hand if they've got any questions. Lloyd, one of our other students, has asked, will the presentation be made available?
Yes, we will. With Kevin's permission, we will make it available.
That's a suitable price, Lloyd. No, we'll find a way of posting this somewhere where people can get it.
Kevin, can we share the presentation with the delegates?
Yes.
Okay, so what I'll do, I'll just create a Dropbox and I'll share it with the delegates.
Yeah, I would just like the PDF of.
Yes, we will PDF it definitely.
Thanks.
Okay. I see we've got
Well, there's
Malcolm.
one question on the Q&A, just asking if you do any work in mining engineering.
So I don't personally, but in looking at the literature for this, there was quite a lot, not so much about mining engineering, but quite a lot about mineralogy. So, but I'm sure if you looked, you would find that there is work being done, I could see, you know, wherever you measure anything, particularly, I guess, in the safety area in mining engineering. So if you've got data and you can use them for prediction, rock burst, that sort of thing, I'm sure that work is being done, and that the techniques are applicable.
Yeah, so I think they're doing some of that work down in Stellenbosch with the geometallurgy and just using machine learning on that. So I think there's also a question from Ilan Malkin.
Yes, hi. I wanted to ask something about data. So firstly, you mentioned the need to get excited data of a higher frequency. So first, what do you mean by excited data? And secondly, from your experience, what is the key to getting good quality data?
So the excited data, I was particularly talking about getting dynamic models. So what we typically do for those sort of models when we're doing empirical models is we come to a plant and we move the inputs up and down by reasonable amounts in an uncorrelated way. So it's a planned experiment to get the responses, the dynamic responses.
I think we may have lost Kevin.
Lost, yes. Yes, Anthony, it looks like we've lost him.
Unfortunately, he's in Egypt at the moment, and the connection is not as strong as it would usually be in South Africa, strangely enough. So hopefully he'll be able to get back online and finish answering that question. But I think essentially in terms of the question you asked, it is having a variety of data, because having 1,000 data points that are all the same doesn't really help you. So if you have a range of your input values and your output values, it'll help quite a lot. Because the one problem with machine learning models is that they can predict from known situations quite well, but anything outside that data set, you can't really trust their predictions very well at all. So unless you have data that works with those particular flow rates, with those particular conditions, it can be very difficult to actually get these kind of machine learning models to work. So I think that's the kind of data set you would be looking for. And and I think that would also inform what your models would be able to predict. So you do need to select your data set quite carefully, and then also be quite careful about what you can and can't predict using those models. Because I think you can fall into the trap of saying, okay, I've got a great model, and then assuming it'll just fit everything very, very well. And I think that's where you also need to be quite careful. So I'll also try and answer the next question. Well, Ilan, did that answer your question?
Yes, it does. Thanks.
So I'll move over to Ian Lipton. You had a question of what input parameters were important in the prediction of the PB content of froth. I assume you're talking about that example from Mount Isa. And we were really looking at the input parameters of the grade coming in. So essentially the total amount of lead and zinc coming in. We were also looking at your flow rates, your air, and your, I think the specific thing we were looking at was the reagent flow rates. So we were looking at using the copper sulfate, the NaSH, and the SEX. to try and then predict what the lead content would be coming out. I think we also had some models where we used the level as well, but it was using only those 5 or 6 inputs. You were able to then get a reasonable prediction of the lead content in the froth and also the zinc content as well. So we had multiple models, one for the lead and one for the zinc. Okay, then we can move to Derek Leroux. You're asking, we used a state-space model, and then did you consider a nonlinear model or a semi-empirical type model with parameters to fit? So I think we did actually use a nonlinear model or a series of nonlinear models. We used nonlinear ARX models, if I'm thinking of the right question or the right paper that you're talking about. We did compare a selection of linear models with nonlinear models, essentially because the extension of that research was to then compare linear MPCs and nonlinear MPCs. But I see Kevin has rejoined. Are you with us again, Kevin?
Sorry about that. I lost connection there for a while.
Yeah, so I was just answering Derek's question where he asked, for the state-space model, we used a linear model in the paper, and did we consider using a non-linear model or a semi-empirical type model?
For the reagents?
Yes, I'm assuming so.
Yeah. Well, the nonlinear ARX is empirical. We haven't done anything semi-empirical because I don't think anyone understands the behavior of that mix of reagents enough to even start writing an equation for it.
Yeah, sorry, I was trying to answer the questions in your stead.
Yes, thanks.
And Ian was asking about the inputs that we used for the lead froth model. For that one, we didn't actually use any parameters from the images. We were just using the inputs that I mentioned. So I'm not sure if that plant actually had the cameras.
So yeah, what I should have said is for the amount of ISO work, I've cheated a little bit by not telling you that we have XRF analyzers on that plant, giving us compositions roughly 15-20 minutes. So that's about the limit. Someone asked about the frequency of the data. That's about the slowest you can use and still get dynamic models, I think, or dynamic models that are useful for control. You can get dynamic models, but they would be of a longer time. The work that I presented on the classification, it's a very complicated feature selection process from the camera, and I didn't have time to talk about that. But I would recommend that paper for anyone who's interested in that sort of work.
Yeah, and then we've got a couple more questions. We've got a question from Lawrence, who's asking, what is your view on feature engineering versus only using inputs that you know should have an impact based on process knowledge?
Yeah, I mean, I think that's an excellent question. And the answer is I don't know. So what I do is both. And then I try and decide which is going to be useful for the particular application that I'm doing. So generally what happens is you use some feature selection algorithm and it comes up with some features that you wouldn't have used and a good fit. and then you use your own knowledge and you get a not so good fit, but at least you understand it. And sometimes you have to kind of mix and match to get a one that you can use. So I think that's still an open question. I mean, what I've taken to doing, Lawrence, because of this problem of it choosing things that I don't think really should be in there, I cut down the data set before I do the feature selection. So I say you can only have these. And try and do it that way. Don't know if that answers the question.
Yeah, I think that we have no more questions in the chat or the Q&A. So I think if everyone is happy, then thank you very much for the presentation, Kevin. It's a very interesting and kind of rapidly changing area, I think.
Yep. No, well, thank you very much from Egypt.
Okay, wait, we've got one more question.
Okay, good.
From Kaya Lebocha. Can the model or tools handle even high volumes and low grades, particularly for the gold tailings industry?
It's also a good question. So the trouble with low grades is sometimes all you've got is it is there or it isn't. So it depends what measurements you have. But, you know, sometimes when you look at some data, it reads 0, 0, and then occasionally it's 0.1. And that's very hard to model because it really doesn't have the right fidelity. But if you've got tailings grades that are well measured, that are accurately measured, and I don't think the volume affects it, I think you can still do things. And then you've always got the other option of modeling the concentrate and then calculating the grade. So it's like a hybrid model. You say, well, I might not get a very good data machine learning model for this tails grade, but maybe I can get the concentrate grade and then calculate the tails grade from it by mass balance. So I certainly wouldn't give up, and I'd look at the data carefully before I started. I see Ilan has his hand up. I don't know if that's just because he hasn't put his hand down or he's still got a question.
No.
Sorry, no additional question.
Okay. No problem.
Okay, in that case, I think we can. Oh, there's another question now from Fiso Kusle. Can modeling be used to store data in coal processing plant where we consider the fines generate RD used and behavior of coal over a period?
Define RDUs for me.
R over D used. I'm not sure what that is.
R over D used. Okay. So,
well, I think we can ask that. Fiso Kusle has been unmuted, so he can expand.
okay.
Oh, hi guys. Can you hear me?
Yep.
Okay, so I'd like to ask, in a processing plant, let's say if you want to store data from using this modeling, like to store historic data, maybe for the RT, maybe the fines generated as you crush coal and the relative density that over period, because as you're mining towards a certain area, the coal will behave differently because of maybe dikes and any geological features. So now essentially what I wanted to understand is that obviously here we're storing multiple data. So that's where I was coming from.
Yeah, I don't think the storing
I
of
don't know
the
if my
data-
question is clear.
Yeah, no, that's fine. I don't think the storing of the data is the issue. Nowadays with clouds and whatever, you can store as much as you like. The challenge is the modeling. So you're talking about underground mining, right?
No, it's actually an open cast.
Open cast mining. Yeah.
Yes, let's say because over time, what I've noticed is that understanding the fines which are generated maybe from poor blasting practice, or maybe from just essentially the movement of machines over the coal in which is intended to be crushed. So I just wanted to know that can this modeling be used to store like different data in order, like let's say, to understand the area in which we're mining now, and then yes, over a period, maybe a year or two, and so forth.
So the predictive ability of any model you wrote now would depend on, have you seen the same kind of ground, the same kind of seams? You talked about the dikes and so on. But yes. I mean, that sounds very interesting to me. That sounds like an effort that's worthwhile. So if you've got the measurements, so you'd say you want to measure fines, or model fines, you have to have a way of measuring it. If you've got that way of measuring it, then it is certainly worth taking some of the data that you have from the open cast mines and seeing what correlates, and I don't know what that might be. Might be the particular kind of truck you're using, massive coal on the truck, or there could be lots of things, or some features of the seams you are blasting, but it would be worth doing, I think.
Okay, thank you. I'm answered. Thanks a lot.
Pleasure.
Yeah, well, we've just crossed over 11 o'clock. So I think we've also seemed to have answered all questions. So hopefully for the final time, thank you very much, Kevin.
Thanks, Anthony. Thanks people for joining.
And thank you for everyone for joining.